Hello, today we'll discuss about the postulates of quantum. So these postulates are basically the backbone of quantum mechanical system. So when you think about a quantum mechanical system, it is basically governed by these postulates. So let me just start with the postulate number 1. In postulate number 1, it is defining the concept of a wave function. The Greek word psi represents the wave function. The wave function is a mathematical function of position in three-dimensional space. This will be represented by r, position and time. So when it's required, you can consider time-dependent system. When it required, when you need, you can use the time-independent system. But the first and the most important part is the idea about the wave function. This wave function represents the idea about the particle. At least mathematically, it can represent the quantum mechanical particle. So now, when you think about that wave function, the mathematical wave function, this must satisfy some of the properties. The properties are, the wave function psi should be continuous, should be single value, should be finite and derivable. Now, what is the meaning of this thing? So if you have a function, so when you are plotting say x in one dimension and you are plotting psi in another. So the function should be smooth in nature. It must be variable, something like this. It is continuous. It should be single values. For a single x value, for the single position value, there will be single value of the psi. This should be single. It should be finite. We really cannot consider an infinite wave function as it is representing the quantum particle. So this should be finite. And it must be derivable. So you can differentiate this function so that you can use this thing in different quantum operations. So this is basically the idea about the quantum wave function. Now, the quantum wave function physically don't have any meaning. Mathematically it is representing wave function, but physically don't have any meaning. So to give a physical meaning of this thing, we need to use the concept of probability density. This is represented in postulate 2. The probability density, say this is represented by E capital P, and this is represented by integration over psi star psi. If it is one dimension, so this is dx. If this is two dimension, dx dy, and if this is three dimension, this is represented by dv or d tau. The probability density says that this should be normalized or this should be 1. Now, what is the meaning of this thing? So first you have to know what is the meaning of psi star. So psi is the wave function. In some of the cases, psi can be a complex number. So complex number means this is in the form of a plus or minus I, b. So there will be a I term. So if you have a function, say having the relation psi is equal to a plus b. So its complex conjugate must be a minus I. So mathematically, this is the idea about the complex conjugate. But in physical world, in quantum physical world, this will be represented as the probability density, probability of finding a particle in certain region. So for depending on the system, it may be one dimension, it may be two dimension, it may be three dimension. So you need to consider the wave function psi within this thing, within the region, and also mathematically we need to calculate what is psi star, the wave function, complex conjugate of this wave function. So to have the idea about whether the particle is confined in this region or not, we need to find the probability density. The probability density will define the particle is confined within this region. So this one sometimes represents the 100% probability. Now comes the next idea about operators. Now in case of dynamics, when you think about a particle moves from one point to another point, it corresponds to its position. So if it is one dimension, this will be represented by displacement x. There will be velocity, corresponding velocity. One can calculate what is acceleration. So then you can calculate kinetic energy, you can get the potential energy, one can get the total energy of the system. Okay, so these are the variables. So in classical world, these are observable or sometimes used to call the physical dynamical variable. So the system is really dynamical system. Now in quantum mechanics, they will be represented by operators. And these operators are linear Hermitian operators. Now the Hermitian operators gives the expectation values of the corresponding function. Now the Hermitian operators are real operators. So when you operate it over the wave function, this will give you the real numerical value. Now, some of the examples of the Hamiltonian or the operators, quantum mechanical operators, Hermitian operators are given. So first is position. In 3 dimensions, if this is represented R, so here this will be represented by some operator. So how to represent operator? Operator will be represented by a crown, a cap. So how to operate? You need to multiply this R with the wave function side. So if you have a operation over the wave function side, so then it will become R into psi. There will be multiplication between R. Same way, if you want to find the momentum operator is P cap. This is minus I H cross tail of del X if you are talking about 1 dimension. If it is not 1 dimension, then you can go for J, K and all. So again the operation will be, so this P will be operated over psi. So when you are operating over psi, so this operation will be there. So this will be simply minus I H cross del X and the psi will be there. So now to get the momentum of the thing, you need to differentiate with respect to position. Now next comes the kinetic energy. So kinetic energy operator, this is given as, so let me just write it as T. So T is given as minus h squared divided by 2m, and instead of one order derivative, this will be d2 dx2. So again, so this will be operated over side. So if you want to find the kinetic energy, so T operator will be operated over wave function. So here there will be second order derivative of psi multiplied with minus h cross by 2. So you will get the kinetic energy of the system. Same way one can find potential energy, total energy is kinetic energy plus potential energy. Potential energy simply multiplication of the potential value with the wave function. So if you know kinetic energy, if you know potential energy, you get the total energy of the quantum mechanical system. Also we can find the angular momentum. This is also a dynamical variable. Next comes the case of eigenvalue. So they are Hermitian operators. So when the Hermitian operators are operated over wave function psi, so the choice of the wave function will be accordingly that the after operation by the Hermitian operator, so you will return back this wave function. You will get that same psi value. And here you will get an eigenvalue. So this eigenvalue must be a real eigenvalue. It's a real one, a real eigenvalue. So in the physical world, in the physical quantum mechanical world, all the dynamical variables are real. So obviously this will be real. So the equation is something like this. You have a operator, any operator, these are the examples of few of these operators. There will be number of operators. So any of these operators is operated over wave function psi. So what will happen? So you will get back this wave function and multiplying with a factor. And this factor, say here I am representing it by lambda. This is known as the eigenvalue. So here if you are operating with kinetic energy, so after operation by kinetic energy, so there will be something left before the wave function. So this will give you the kinetic energy of the system. If it is operated by momentum operator, so then this will be the eigenvalue of the momentum. And this must be real as our operators are Hermitian. And the last one, here this is known as the expectation value, or you can think about the average value. What is the meaning of this thing? So normally when you perform any experiment, you need to get a set of values. So you are finding position. So you get a set of values, say x1, x2, x3, x4, up to a certain value, say x2. Now then what you wish to do is to find the average of all of this. So in the quantum mechanical world, the idea is almost similar. So if you have a region where you are trying to find the electrons or try to find the quantum mechanical particles. So within that region, you need to perform number of experiments to get the position. Say after first experiment, you will get the position x1. Then you will have a second position, third position, fourth position, and up to nth position. Number of n times you have run the experiment and you have got the set of data. And you need to find the average of all. So in quantum mechanical world, the expectation value is giving you the average of this. Now here, this average of the expectation value will be calculated like this. Say you want to find the operator. That's mean, say if you want to find the momentum. So how to find this thing? How to find the momentum operator? So for that case, you need to follow this relation. So this is the expectation notation. So there will be integration over psi star, this operator psi within the range. If this is one dimension, this will be. Now how to operate this thing? So first momentum operator will be operated over wave function. So momentum operator is minus I h cross del x. So first there will be this operation. Then this factor will be multiplied with complex conjugate of the wave. Then find the integration. What will give us? This will give us the expectation value of this quantum mechanical system or quantum mechanical operator system. So these are 5 important postulates of quantum mechanics. So what are those? So the first one, define what is the basic idea about wave function. Now what is the physical meaning of a wave function? This is given at postulate 2. What is the idea about dynamical variable or the Hermitian operators? This is given in postulate 3. Now how to get that eigenvalues of this corresponding operators? This is given in postulate 4, and in postulate 5 it gives the idea about the average value. Now depending on this, one can take any of the quantum mechanical system and one can solve the problem. So here we need to solve the Schrodinger's wave equation. Now to do this thing, so we are going to get a simplest example of a particle confined in a one-dimensional potential box. So what is the meaning of this thing? Say if you have a one-dimensional distance of 0 to L. So here at x equal to 0 and x equal to L, the potential is infinite. And within that length 0 to L, so particle is confined with potential value 0. So within this range, so particle is acting like a free particle. So you may think about particle starts from this point and it moves up to a length L. It may keep on oscillating like this. So it's a problem of a one-dimensional system. Now here, how to do these things? How to solve the problem? So first you need to get the wave function. It's a quantum mechanical system. First you need to get the wave function. So how to get the wave function? So to get the wave function, we need to solve the Schrodinger's wave equation. So what is the Schrodinger wave equation? This is Hi is equal to. So the Hamiltonian operator will be operated over wave function, and by using this you can get the wave function. So one-dimensional Schrodinger wave equation is given by this expression, where E represents the total energy and V represents the potential energy. So one can modify the equation according to the problem, but potential energy is 0 within the length. So one can write a equation of the Schrodinger wave equation for the distance 0 to L. So the equation will be given as. So one can just rearrange the thing and you can get a expression something like this: d2 psi dx2. Okay, you can multiply with this thing and take it in other side. So this will be plus of 2m divided by h square. This is E psi. This is equal to 0. Now here psi was considered as a function of position and it's considered as a time independent. So it's a second order derivative. So one can solve it, and by using the boundary condition. What are the boundary conditions? That at the potential point, at the potential boundary point, at x equal to 0 and x equal to L, the potential values are infinite. So they are confined within distance. So by using the boundary conditions, one can solve this Schrodinger wave equation. And if you are able to solve this thing, and then by using the concept of probability density, one can get the expression for the wave function as √2 by L sine n by x. Now n represents the different possibilities. So it may happen that n is equal to 1, so we will get the corresponding energy states. If this is n equal to 2, so you will get the second energy states and its corresponding wave function. If you are able to find the wave function, and then one can get what is the energy of the system. Now the most important part is if you know the wave function, then you can get what is the momentum of the system. What is position of the system? Okay, what is kinetic energy of the system? All the things you can get. If it's required, you can get the expectation value of momentum, expectation value of position, expectation value of any of the operator you can get when you have this wave function chart. And if it is required, you can get what is the energy of the system. So by using the concept of quantum postulate, one can get idea about the quantum mechanical system, any of the quantum mechanical system. Okay, thank you.